Hello everyone. I am Dr.E.Purushotham, Associate Professor, Department of Physics, School of Sciences and Humanities. Today, I am going to discuss laser. So the full form of laser is light amplification by stimulated emission of radiation. So today I am going to discuss about that laser and laser working principle. What is the main differences between ordinary light and laser light? What is the working principle of laser? What is absorption, spontaneous emission of radiation, and stimulated emission of radiation? So, you know very well, laser, light amplification by stimulated emission of radiation. So, SCR is the, in laser, you can see, so you see in laser, SER is the working principle of laser, light amplification by stimulated emission of radiation. Laser is an light amplification by stimulated emission of radiation. The laser is a device to produce a strong monochromatic, collimated, and highly coherent beam of light, and depending on the phenomena of stimulated emission of radiation. Stimulated emission of radiation. You see here the laser introduction. The word laser is an acronym for light amplification by stimulated emission of radiation. It is a powerful monochromatic light source of collimated beam in which the light waves are highly coherent. The laser light has many superior features compared to conventional light or ordinary light source. Einstein introduced this concept in 1917. Dr. D.H. Mayman demonstrated the first laser, namely the ruby laser, in the year of 1960. So clearly, you can see here laser full form. So laser L, light amplification by stimulated emission of radiation. So you can see here LASER. Before laser, it was called maser. Microwave amplification by stimulated emission of radiation. But these are not microwaves, these are light waves. So, light amplification by stimulated emission of radiation. What is that? The word laser is light amplification by stimulated emission of radiation. The working principle of laser, stimulated emission of radiation. Stimulated emission of radiation. Actually, compared to ordinary light, the laser light emits the radiation only in one direction with phase relation and frequency relation. But ordinary light emits the radiation in all the directions without phase relation and without frequency relation. The main difference between ordinary light and laser light. So, the ordinary light emits the radiation in all the directions, but laser light emits the radiation only in one direction with a phase relation and frequency relation. So characteristics of laser. Laser differs from the ordinary light with respect to some properties. They are coherence, monochromaticity, directionality, intensity. The laser light is a high coherent, monochromatic, high directional, high intense light ray. That is a laser light. So compared to ordinary light or conventional light, what are the examples of ordinary light? So tube light, sunlight, candle light, etc. So the laser light, comparing with the ordinary light, laser differs from the ordinary light with respect to some properties. They are coherence, monochromaticity, directionality, and intensity. So, what is coherence? The property of existing either zero or constant phase angle difference between two or more waves are called coherence. You can see here the property existing either zero or constant phase angle difference between two or more waves are called coherence. A predictable correlation of the amplitude and phase at any one point with other point is called coherence. The light from a source consists of wave pattern. These wave pattern, when identical in phase and direction, are called coherent. So two wave fronts. For example, if you imagine two wave fronts, the two wave fronts are having the same wave, same frequency, same amplitude, or same phase angle difference. So that is coherence. The property of existing either zero or constant phase angle difference between two or more waves. So two or more waves are having same amplitude, same frequency, same phase difference. Then the light waves are called coherent light waves or simply coherence. A predictable correlation of the amplitude and phase at any one point of with other point is called coherence. The light from a source consists of wave pattern. Wave pattern. Take one wave pattern and another wave pattern. Take the correlation between phase, frequency, and phase angle difference. If they are having same values, that is the coherent light. Laser has a high degree of coherence than the ordinary light source. The coherence of laser emission results in an extremely high power of 5 into 10 to the power 6 watt per meter square. A laser beam can be focused to a very small area of about zero point 0.7 micrometer diameter. Zero point 0.7 into 10 to the power minus 6 meters. That is zero point 0.7 micrometer diameter. Coherence, two types. Types of coherence, you can see types of coherence. So coherence is of two types: spatial coherence and temporal coherence. What is spatial coherence definition? You can observe here. So spatial coherence. What is the spatial coherence? The property definition, the property of existing either zero or constant phase angle difference up to here same phase angle difference between two points on the different wave fronts. So you can see this is one wave, this is another wave. So this is P1, this is P2, P2. So what is the definition? The property of existing either zero or constant phase angle difference between two or more waves are called coherence. But spatial coherence, the property existing either zero or constant phase angle difference between two points on the different waves are called spatial coherence. Spatial coherence. Try to understand. What about temporal coherence? This is the one wave P1.1, P2.2. These are the two different points on the same wave. But spatial coherence, two points P1, P2 on the two different waves. But temporal on the same wave, two points. You try to understand. So temporal coherence definition, the property of existing either zero or constant phase angle difference between two points on the same wave is called temporal coherence. Temporal coherence. So try to understand coherence spatial coherence, temporal coherence. What is coherence? The property of existing either zero or constant phase angle difference between two or more waves are called coherence. Coherence is divided into two types: spatial coherence and temporal coherence. So, spatial coherence, I am telling only definition: coherence, spatial coherence, and temporal coherence. So, try to understand. So, spatial coherence, the property of existing either zero or constant phase angle difference between 2 points P1, P2 on the two different waves, that is called spatial coherence. Temporal coherence, the property of existing either zero or constant phase angle difference between 2 points P1, P2 on the same wave, that is called temporal coherence. Temporal coherence. A predictable correlation of amplitude and phase at any one point with the other point is called coherence. Another definitions. The light from a source consists of wave pattern. So another definition, these wave patterns when identical in phase and directions are called coherence. Coherence. Laser has a high degree of coherence. It has high coherent or high degree of coherence. High degree of coherence. So spatial coherence, the property of existing either zero or constant phase angle difference between 2 points on the two different waves are called spatial coherence. So temporal coherence, the property of existing either zero or constant phase angle difference between 2 points on the same wave, that is called temporal coherence. Okay, next, directionality. Directionality. So simply try to understand, for ordinary light, I am giving here OL, ordinary light, or CL, conventional light, LL, laser light. The ordinary light emits the radiation in all the directions without phase relation, without frequency relation. But the laser light emits the radiation only in one direction with phase relation and frequency relation. So the light ray coming ordinary light source travels in all the directions. You can see clearly here, it can travel in all the directions. But laser light to travel in a single direction. You try to understand, this is single direction. This is the main difference. The ordinary light emits the radiation in all the directions. It can move, it can travel in all the directions. But laser light travels only in single direction. So, for example, the light emitted from the torch, the light emitted from torch spreads 1 kilometer distance. You see, nearly spreading area 1 kilometer also. But the laser light spreads a few centimeter, 1 centimeter per 1 meter per meter, or 1 millimeter per meter. It is very less compared to ordinary light. But the laser light spreads a few centimeter distance, even it travels longer distance. The ordinary source emits light in all the directions, and its angular spread is 1 meter by meter. But the laser is highly directional and non-divergent, and its angular spread is 1 millimeter per meter. So you can see here, for example, this is ordinary light, OL, ordinary light. This is laser light. If you are observing, you try to understand, for example, this is a torch light or ordinary light. If we are observing at a distance of 1 kilometer, the spreading area is also nearly 1 kilometer. Its spreading area is more. But you can understand here in laser light, it can move only in single direction. So this spreading area is very less, near 1 centimeter. 1 centimeter, you can see. So this is the laser beam. Laser is moving only in one direction. We are moving, rotating all the directions, but the laser light you try to see in any direction, it is giving very less spreading area. Very less spreading area. So you see here, this is a torchlight. Torchlight. You clearly observe the spreading width. How much? So it is more the ordinary light. It is a ordinary light. This ordinary light emits the radiation in all the directions. That spreading width is more. You can understand. The light ray coming ordinary light source travels in all the directions. But laser light, you can see this is the laser light. Laser light you can see only in one direction. Clearly, you try to understand both ordinary light and laser light. Ordinary light and laser light. The light ray coming from ordinary light source travels in all the directions, but laser light travels in single direction. For example, the torch light emitted light ray spreads nearly 1 kilometer distance. At a 1 kilometer distance, if we are observing, the width is also nearly 1 kilometer, but the laser light spreads a few centimeters distance. Even it travels longer distance. You can try to understand here. So this is ordinary light. This is laser light. At a 1 kilometer distance, this spreading width is also nearly 1 kilometer. You can see here. Same distance, if you are observing at 1 kilometer distance, this spreading area is very less. This is 1 centimeter. So laser light we can be observed in PPT. You can see clearly. So I am taking example torchlight for ordinary light. This is torchlight. Torchlight is the ordinary light. It emits the radiation in all the directions. So try to understand. Try to understand ordinary light. Examples: torchlight, sunlight, tube light, candle light, etc. Ordinary light. The ordinary light emits the radiation in all the directions without phase relation and without frequency relation. But the laser light emits the radiation only in one direction with phase relation and frequency relation. So you try to understand that one. The light ray coming ordinary light source travel in all the directions, but laser light travels in a single direction. That is the main difference. For example, I am taking torch light. The light emitted from torch spreads 1 kilometer distance. You can see from this to this nearly 1 kilometer. Nearly this is 1 kilometer. But this spreading area is very less. Very less. Spreading area is very, very less. This spreading area is very less. So try to understand this one. The ordinary source emits light in all the directions and its angular spread is 1 meter. Its angular spread is 1 meter by meter. But the laser is highly directional and non-divergent and its angular spread is 1 millimeter by meter. So this is the directionality. So laser light has the high directionality. Laser light is a high directional light. High directional light. So directionality, in this directionality, we can discuss about, so this is, we can discuss about divergence. What is divergence? The divergence tells how rapidly the beam spreads when it is from the laser. That is divergence. The divergence tells how rapidly the beam spreads when it is from the laser. If from the laser beam is coming out, how rapidly the beam spreads, it represents divergence. So the divergence is known as rapidly the beam spreading when it is from the laser. So the beam divergence represented by phi. Phi is equal to 1.22 lambda by W naught. So that is W naught is the spot size, terms of spot size. So this is the laser source. From laser source to this is D1, this is D2, D2. So the spot's diameter, it represents diameter A1, this diameter A2. Let D1 and D2 are the distances from the laser window. From the laser window. If the diameter of the spots are measured to be A1 and A2 respectively, then phi is equal to A2 minus A1 by 2 into D2 minus D1. So clearly try to understand divergence. The divergence tells how rapidly the beam spreads when it is from the laser. Okay, number one, the beam divergence represented by phi. Omega naught is the terms of spot size. From the laser, D1 and D2 are the distances from the laser window. If the diameters of the spots are A1 and A2, therefore divergence phi is equal to A2 minus A1 by 2 into D2 minus D1. Divergence we can also calculate in terms of lambda and omega naught. That is 1.22 lambda by omega naught. And the second one we can calculate divergence using the A1, A2 diameters of the spots and D1, D2 are the distances from the laser window. Phi is equal to A2 minus A1 by 2 into D2 minus D1. Monochromaticity. Monochromaticity. So the laser light is more monochromatic than that of conventional light source. This may be due to stimulated characteristics of laser light. The bandwidth of the conventional monochromatic light source is nearly 1000 angstroms. But the bandwidth of monochromatic light source is nearly 10 angstroms. But the bandwidth of ordinary light source, this is 10,000 1000 angstroms. So take an x-axis wavelength on y-axis intensity. The delta lambda bandwidth or monochromatic light source in ordinary light. Ordinary light has all the colors. This is ordinary light. Ordinary light has the all colors. It has all the colors. So it has all wavelengths. So the bandwidth delta lambda is equal to nearly 1000 angstroms. Nearly 1000 angstroms. This width is more 1000 angstroms. But laser light has laser light has only single color. So it has only same one wavelength. So this width is nearly 10 angstroms. So delta lambda width is equal to 10 angstroms. Clearly try to understand. So monochromatic light source width 10 angstroms, ordinary light source 1000 angstroms, 1000 angstroms. The laser light is more monochromatic than that of conventional light source. This may be due to the stimulated characteristics of laser light. The bandwidth of conventional monochromatic light source is the bandwidth of monochromatic light source is 10 angstroms, but the bandwidth of ordinary light source is 1000 angstroms. For high sensitive laser source is 10 to the power minus 8 angstroms. You try to understand here, we are taking an x-axis lambda wavelength on y-axis intensity. So here also same, you can see here on x-axis lambda, on y-axis intensity. So for ordinary light or conventional light source have all the colors. So means these are having all wavelengths. So the bandwidth is also more compared to laser light. So this is 1000 angstroms. This is for ordinary light. For laser light has only single color. So it has only one wavelength. So it has only one wavelength. That width is also very less. Delta lambda is equal to 10 angstroms. You can see here also. Delta lambda for ordinary light 1000 angstroms. This is for laser light 10 angstroms. 10 angstroms. Laser beam is highly monochromatic. It emits a single wavelength, one color. You can see clearly. Already I discussed. Laser beam is highly monochromatic. It emits a single wavelength and single color or one color because atoms or molecules are transition between two energy states. Hence, it possesses good spectra since range of laser beam wavelength delta lambda is very narrow, nearly 10 angstroms. But ordinary light source emits combination of wide range of wavelengths or colors. Because atoms or molecules are transition from several number of excited states to ground state. So it emits different energies. Therefore, it is polychromatic light wave. So what is monochromatic? Mono means single, chromatic means wavelength. So monochromatic means single wavelength. The laser light is more monochromatic than the conventional light source. This may be due to the stimulated emission of radiation or stimulated characteristics of laser light. The bandwidth of conventional monochromatic light source is nearly very narrow, nearly 10 angstroms. But the bandwidth of ordinary light source is very high or wide range, that is nearly 1000 angstroms. For high sensitive laser source is that is 10 to the power minus 8 angstroms. Ordinary light emits all the colors. So it has all wavelengths. So the width is also more. Width delta lambda is equal to 1000 angstroms. For monochromatic light or laser light has only single color. So it has only single wavelength. Therefore, the width is also very small or very narrow. that is delta lambda is equal to 10 angstroms. So laser beam is highly monochromatic. It emits a single wavelength or one color because atoms or molecules are transition between two energy states. Between two energy states, for example, this is E1, this is E2, two energy states. Hence, it possesses good spectral since range of laser beam wavelength delta lambda is very narrow. But ordinary light emits, for example, it is jumping from higher to lower. It gives only single wavelength. E2 minus E1 is equal to hc by lambda. It gives only single wavelength. But in ordinary light emits the combination of wide range of wavelengths, all colors. It has all colors because atoms or molecules are transition from several number of excited states to ground state. Only one energy level to ground state. It gives only single color, single wavelength. But ordinary light atoms or molecules are transition from several number of excited states to ground state. So it emits different energies. Therefore, it is polychromatic. Polychromatic. Intensity. Laser light is highly intense than the ordinary light. This is because of coherence and directionality of laser. The ordinary light spreads in all the directions. So the intensity reaching the target is very, very less. But in the case of laser light, due to the high directionality, the intensity of laser beam is concentrated in a small region. This concentration of energy gives a high intensity since in laser many number of photons are in phase with each other. The amplitude of the resulting wave becomes Na. One wave amplitude is A. N number of waves are coming, that is N into A, and hence the intensity of laser is proportional to intensity is proportional to N square A square. It is estimated that light from a typical 1 milliwatt laser is 10,000 times brighter than the light from the sun at the Earth's surface. So, simply you try to understand ordinary light. Distance increases from the source, the intensity decreases. But laser light is not depending on the distance. At any place, it has the high intensity. High intensity. So you can see here ordinary light spreading you can observe simply. So compared to laser light, ordinary light emits in all the directions. Laser light is highly intense light. So it has high directional, high coherent light. The ordinary light spreads. You see, the ordinary light spreads in all the directions. You can see in that figure. So the intensity reaching the target is very less. Also, you can observe. At the starting, very bright. The light rays are moving. The intensity is decreasing. You clearly observe in this figure. Since in laser, many number of photons are in phase with each other, the amplitude of the resulting wave become n into a. So the intensity increases. I is directly proportional to n square a square. Next, what is the main differences between ordinary light and laser light? So ordinary light are Polychromatic since it consists of radiations of several wavelengths. Ordinary light emits the radiation in all the directions. It has all the colors. It has the several wavelengths. But laser light is monochromatic since it consists of only single wavelength. So ordinary light consists several wavelengths. Laser light consists only single wavelength. Ordinary light is divergent because it spreads in all the directions. Ordinary light emits the radiation in all the directions without phase relation and without frequency relation. But laser light is non-divergent because it travels in single direction. The laser light emits the radiation only in single direction with phase relation and frequency relation. Next point. Intensity of ordinary light is lesser because concentration of photons is lesser. So here intensity of laser light is higher because concentration of photons is higher. Ordinary light is not coherent, but laser light is highly coherent. Due to the less intensity, brightness of the ordinary light is low. Brightness of ordinary light is low because due to the less intensity, the ordinary light has less intensity. The brightness of ordinary light also very slow or very low, very less. Due to the high intensity, brightness of laser light is high. So examples of ordinary light: sunlight. Example here: laser light, helium neon laser, ruby laser, semiconductor laser. So many types of lasers are there. So you can see here again I am discussing distinguish between ordinary light and laser light. Ordinary lights are polychromatic since it consists of radiation of several wavelengths. Laser light is monochromatic. Simply you can say ordinary light is polychromatic. Laser light is monochromatic. Ordinary light is divergent. Laser light is not divergent. Ordinary light spreads the radiation in all the directions. Laser light emits the radiation only in single direction. Next, intensity of ordinary light is lesser. Intensity of laser light is higher. Ordinary light is not coherent. Laser light is highly coherent. Due to the less intensity, the brightness of ordinary light is also very less. Due to the high intensity, brightness of laser light is also high. Examples of ordinary light: sunlight, candle light, etc. Laser light, example laser light, that is helium neon laser, semiconductor laser, and so on. So in laser, I'm going to discuss about basic definitions. What are the basic definitions? Absorption. It is also called stimulated absorption of radiation. Spontaneous emission of radiation, stimulated emission of radiation, population inversion, and pumping. Lifetime metastable state we are going to discuss. What is spontaneous? In your own words, what is stimulated? Spontaneous means by itself without applying any force. Stimulated with applying some force. That is stimulated. Now, I am going to discuss about the basic definitions. So, absorption or stimulated absorption of radiation, spontaneous emission of radiation, stimulated emission of radiation, population, population inversion, and pumping. In that also, we need to learn lifetime metastable state. First one, absorption or stimulated absorption of radiation. So absorption, before that, what is ground state and excited state? We are going to discuss about that one. So you can see I am giving this option, pen option, right. So for example, you see this one, this is energy level E1, ground state. This is ground state. This is E2, excited state. So ground state energy E1, excited state energy E2. So what is ground state? The lowest energy level. The lowest energy level for an individual atom occurs when its electrons are all in the nearest possible orbits to its nucleus. This energy level is called ground state. Again, you try to see the lowest energy level, that is E1, the lowest energy level for an individual atom occurs when its electrons are all in the nearest possible orbits to its nucleus. This energy level is called ground state. What about excited state? When one or more of an atom's electrons have absorbed energy, they can move to outer orbits, and the atom is then referred to as being excited, and that energy levels is called as excited state or excited state energy. It is represented by E2. Excited states are generally not stable. As electrons drop from higher energy level to lower energy levels, they emit the extra energy as light photon or light. So, for example, this is the positively charged nucleus. The electrons are revolving around the positively charged nucleus. We know very well. So, this is outermost shell orbit. This is outermost shell orbit. So here you see this is the nearest. You see here the electrons are in nearest possible orbits to the nucleus. This is nearest. We can see. So clearly you try to understand this is positively charged nucleus. Around this positively charged nucleus, the electrons are revolving in certain orbits. So this is outermost shell, outermost shell orbits, outer orbits. These are outer orbits. You can see here outer orbits, and the atoms then refers to being excited. This is the nearest, you see, nearest possible orbits. We can write here nearest possible orbits. Orbits. So you see the lowest energy level for an individual atom. If you want to take, this is E1, that is nearest possible orbit. It is represented by E1, that is lowest energy or ground state energy. This is excited state. At outer orbits, the electron can move from nearest possible orbit to higher energy levels. Higher energy levels. So you see clearly the lowest energy levels for an individual atom occurs when its electrons are all in the nearest possible orbits to its nucleus. This energy level is called ground state. When one or more atoms electrons have absorbed energy, they can move to outer orbits. For example, this is nearest, the electron is here. The electron absorbs the energy, it can move to outer orbits. It can move to outer orbits. So the electrons can move to higher energy levels, and the atom is then referred to as being excited, and that energy level is called as excited state. Excited states are generally not stable. The excited state atom cannot stay long time, so it is not stable. It can return to the ground state by itself and by stimulated. The excited state atom cannot stable in the excited state. As electrons drop from higher energy level to lower energy level, they emit the extra energy of light, that is E2 minus E1 is equal to h nu photon energy. So the electron drops from higher energy level to lower energy level. This is higher E2, lower E1. If it is moving from higher, this is E2, this is E1. So E2 minus E1, E2 minus E1, this is E2 minus E1 is equal to h nu. So the extra energy, you can see extra energy as light it emits. The electron jumps or drops from higher energy level to lower energy level, higher energy level to lower energy level. It emits the radiation or light photon, that is E2 minus E1 is equal to h nu. H nu. So you can see here, what is this absorption or stimulated absorption? You clearly observe here, this energy. This is energy E2 minus E1 is equal to h nu. Photon energy is incident on the ground state atom. The ground state atom absorbs all the photon energy and goes to higher energy level. Phenomena is called absorption. So you can see clearly E2 minus E1 is equal to h nu photon energy. Photon energy. You see, this energy is coming, energy is incident on the ground state atom. The ground state atom absorbs all the photon energy. The ground state atom absorbs all the photon energy and goes to higher energy levels. Higher energy levels. This phenomena is called absorption, or simply we can say the energy is incident on the ground state. The atom stimulates from lower energy state to higher energy level. Phenomena is called stimulated absorption of radiation. You can see clearly E2 minus E1 is equal to h nu photon energy is incident on the ground state atom. The ground state atom absorbs all the energy and it stimulates from lower energy state to higher energy state. Phenomena is called stimulated absorption of radiation. Of radiation. So you can see clearly definition. Definition. So what is the definition? I want to give here definition. E2 minus E1 is equal to h nu photon is incident on the ground state atom. The ground state atom absorbs all the photon energy. Then it stimulates from lower energy level to higher energy level. Phenomena is called absorption or stimulated absorption of radiation. Already we observed here clearly the energy E2 minus E1 is equal to h nu photon energy is incident on the ground state atom. The atom absorbs all the photon energy and goes to higher energy levels. You can see the atom is moving from lower to higher energy state. Okay, this is the definition. What is the definition? E2 minus E1 is equal to h nu photon is incident. Photon energy is incident on the ground state atom. The ground state atom absorbs all the photon energy and stimulates from lower energy level to higher energy levels phenomena is called absorption or stimulated absorption of radiation. So explanation you try to understand, let E1 and E2 are the energies, and this is N1, this is N2. N2. N1 and N2 are the number of atoms per unit volume of ground and excited state. Excited state. So actually, N is the population. Population. What is the definition of population? The number of atoms per unit value. The number of atoms per unit volume is called population. So N1 is the population in ground state. N2 is the population in excited state. E1 is the ground state energy. E2 is the excited state energy. Excited state energy. You can see clearly, try to understand. E1 and E2 are the energies, and N1 and N2 are the number of atoms per unit volume of ground state, N1, and this is excited state. Simply, we can say N1 is the population in E1, N2 is the population in E2. E1 means ground state energy, E2 means excited state energy. Population means the number of atoms per unit volume. The number of atoms per unit volume. So E1 and E2 are the energy levels. That is, this is ground state energy E1, E2 is the excited state energy. N1 is the population in E1, N2 is the population in E2. Rho V is the density of photon density, or rho V, you can see number of photons per unit volume. Number of photons per unit volume. You can see this is density of photon density, or it is also known as number of photons, per unit volume. We can say that number of photons per unit volume. Number of photons per unit volume. Suppose if a photon of energy E2 minus E1 is equal to h nu, this is E2 minus E1 is equal to h nu, interact with an atom present in the ground state or incident on the ground state atom, the atom gets excitation. Why it gets excitation? The atom absorbs all the photon energy and it gets excitation. From ground state to excited state, from ground state to excited state, the atom can move by absorbing the photon energy. It is the process of excitation of atom into excited state from ground state by absorbing the incident photon. So what I am saying, try to understand here. This is E1, this is E2, this is N1, this is N2. Here also, this is N1, this is N2. This is before interaction of photon, this is after interaction of photon. Or before incident photon on the ground state atom, after incident the ground photon on the ground state atom. Let E1 and E2 are the ground state and energy state energies. N1 is the population in E1, N2 is the population in E2. E2. If E2 minus E1 is equal to h nu photon is incident on the ground state atom, The ground state atom absorbs all the photon energy and goes to higher energy level. Phenomena is called absorption or stimulated absorption of radiation. Radiation. So let E1 and E2 are the energy levels at ground state and excited state. N1 is the population in E1, N2 is the population in E2. If E2 minus E1 is equal to h nu photon is incident on the ground state atom, the ground state atom absorbs all the photon energy and goes to higher energy state. That is called absorption or stimulated absorption of radiation. We can see clearly in this figure also. So, stimulated absorption rate depends upon the number of atoms available in the lowest energy state as well as the energy density photons. So at ground state, the number of stimulated absorptions depending on ground state population N1 and number of number of photons per unit volume rho v. Rho v. What I am saying here, the stimulated absorptions depending upon population at ground state and also rho v. So you see here the stimulated absorption rate is directly proportional to N1. N1 is the population at ground state and also directly proportional to rho v. Rho v is the number of photons per unit volume. So we can write here directly proportional to rho v into N1. So proportionality constant B12 into rho v N1, where this B12 is known as Einstein's coefficient of stimulated absorption. The proportionality constant B12 is known as Einstein's coefficient of stimulated absorption. Stimulated absorption. So you can see here clearly you can see here stimulated absorption. So this is the energy is coming, that is E2 minus E1 is equal to h nu photon energy is incident on the ground state atom. You can see the energy is coming. It is incident on the ground state atom. So the ground state atom absorbs all the photon energy. It moves from lower energy levels to higher energy levels. This is E1, this is N1. So this is E2, this is N2. You can see. So it is moving from N1 to N2, lower energy level to higher energy levels. You can see E2 minus E1 is equal to h nu photon energy is incident on the ground state atom. It absorbs all the photon energy and moves to lower energy state to higher energy state. Phenomena is called stimulated emission of stimulated absorption rate or absorption. Stimulated absorption. Okay, coming to second one, spontaneous emission. Spontaneous emission of radiation. Spontaneous emission of radiation. You see here the spontaneous emission of radiation. You clearly try to understand here. This is excited state atom. The excited state atom cannot stay long time. It can stay up to 10 to the power minus 8 seconds. After 10 to the power minus 8 seconds, the atom returns to the ground state by itself. This phenomena is called spontaneous emission of radiation. Spontaneous emission of radiation. You can see here spontaneous emission of radiation. So definition, In the excited state, this is excited state. In the excited state, the atom can stay up to 10 to the power minus 8 seconds. In the excited state atom cannot stay long time. It can stay up to 10 to the power minus 8 seconds is called lifetime. The atom staying time in the excited state is called lifetime. So the lifetime of excited state atom is up to 10 to the power minus 8 seconds. In the excited state, the atom cannot stay long time. It can stay up to the power 10 up to the 10 to the power minus 8 seconds. After 10 to the power minus 8 seconds, the atom returns to ground state by itself. You can see returns to the ground state by itself. This phenomena is called spontaneous emission of radiation. Spontaneous emission of radiation. You try to understand here. The excited state atom does not stay in a long time in the excited state. The lifetime of excited atom in the higher state, that is excited state, E2 is up to 10 to the power minus 8 seconds. After the lifetime, it means after 10 to the power minus 8 seconds, the excited atom gets de-excited into the ground state by emptying the photon of energy. Emptying the photon of energy. So you see, this is the ground state population N1. This is the excited state population N2. Let us consider E1, comma E2 are the two energy levels. E1 is the excited state, E2 is the E1 is the ground state, E2 is the excited state. Let us consider two energy levels, E1 and E2. E1 is the ground state energy, E2 is the excited state energy. N1 is the population in E1, N2 is the population in E2. E2. So in the excited state, the atom can stay up to 10 to the power minus 8 seconds only. It is called lifetime. So after 10 to the power minus 8 seconds, the atom returns to the ground state by itself with emptying E2 minus E1 is equal to H nu photon. This phenomena is called spontaneous emission of radiation. It is the process, you see clearly, it is the process, the de-excitation of atom itself into ground state after its lifetime from the excited state. The excited state atom cannot stay long time. It returns to the ground state by due to the de-excitation. So the spontaneous emission rate is directly proportional to population N2 at a higher energy level. So proportionality constant A21, where A21 is known as Einstein coefficients of spontaneous emission. Spontaneous emission of radiation. So spontaneous emission of radiation. What is the definition? Already we discussed. What is the definition? In the excited state, the atom cannot stay long time. It can stay up to 10 to the power minus 8 seconds. After 10 to the power minus 8 seconds, the atom returns to the ground state by itself. The atom returns to the ground state due to the de-excitation with emptying E2 minus E1 is equal to photon energy. This phenomena is called spontaneous emission of radiation. So spontaneous emission radiation is directly proportional to N2, that is population in excited state. So A21, proportionality constant A21, where A21 is the Einstein's coefficients of spontaneous emission of radiation. So this is N1, this is N2. Characteristics of spontaneous emitted radiation. The emitted radiation is polymonochromatic. It has all colors, all wavelengths. So monochromatic. The emitted radiation is incoherent. It is not a coherent light. So the emitted radiation is less intense. So it has very less intensity. The emitted radiation has less directionality. Example, light from sodium or mercury lamp or tube light or sunlight or candle light. So try to understand again spontaneous emission of radiation. The excited state atom cannot stay long time. It can stay up to 10 to the power minus 8 seconds. After 10 to the power minus 8 seconds, the atom returns to the ground state by itself or due to the excitation with emptying photon. Phenomena is called spontaneous emission of radiation. So the excited state, you can see here, let E1 and E2 are the two energy levels. E1 is the ground state, E2 is the excited state, N1 is the population in E1, N2 is the population in E2. So the atom can stay up to 10 to the power minus 8 seconds. After 10 to the power minus 8 seconds, the atom returns to the ground state by itself or due to the de-excitation. This phenomena is called spontaneous emission of radiation. The spontaneous emission radiation is depending on excited state population N2. So proportionality constant A21, it is called Einstein's coefficient of spontaneous emission of radiation. So the characteristics of spontaneous emitted radiation. The emitted radiation is polymonochromatic. The emitted radiation is incoherent. It has less intensity. So the emitted radiation has less directionality. Spontaneous emission of radiation. Examples, light from sodium or mercury lamp. So you can also try to understand here stimulated emission also we can. Next one, we are going to discuss about stimulated emission of radiation. Stimulated emission of radiation we can observe. So for example, in the excited state, the atom can stay up to the power up to 10 to the power minus 8 seconds. So before 10 to the power minus 8 seconds, if E2 minus E1 is equal to h nu photon energy is incident on the excited state atom, the excited state atom stimulates from higher energy level to lower energy level with emitting two photons. One is incident photon and the second one is emitted photon. Emitted photon. You try to understand. So already we discussed in spontaneous emission of radiation. In the excited state, the atom cannot stay long time. The atom staying time is known as lifetime. The lifetime of excited state atom, that is 10 to the power minus 8 seconds, up to 10 to the power minus 8 seconds. After 10 to the power minus 8 seconds, the atom returns to the ground state by itself. Phenomena is called spontaneous emission of radiation. Before 10 to the power minus 8 seconds, if E2 minus E1 is equal to h nu photon is incident on the ground excited state atom, the excited state atom stimulates from higher energy level to lower energy level with emitting two photons. One is incident photon, another one is emitted photon. The incident photon and emitted photon are having same frequency, same amplitude, same phase angle difference. These are having high coherent, high directional, monochromatic. These are having high intensity. This phenomena is called stimulated emission of radiation. Stimulated emission of radiation. So what I am saying the definition before 10 to the power minus 8 second, E2 minus E1 is equal to h nu photon energy is incident on the excited state atom. The atom stimulates from higher energy level to lower energy level with emitting two photons. Phenomena is called stimulated emission of radiation. The emitted photon and instant photon. In this process, it gives two photons. One is incident and another one is emitted. These two photons are having same frequency, same amplitude, same phase angle difference. This light ray emits the radiation only in one direction with phase relation and frequency relation. These are high coherent, high directional, monochromatic, high intensity radiation. So this radiation is known as stimulated emission of radiation. This is stimulated emission of radiation. You can see here stimulated emission of radiation. Clearly try to understand. So in the excited state, this is the atom. So one E2 minus E1 is equal to h nu photon is incident on the excited state atom. We can see clearly, you can see this atom is moving due to the stimulated absorption moving higher energy level. In the higher energy level, E2 minus E1 is equal to h nu photon is incident on the excited state atom. The excited state atom stimulates from higher energy levels with emitting two photons. One is incident photon and the second one emitted photon. Emitted photon. This phenomena is called stimulated emission of radiation. Try to understand clearly. You see, E2 minus E1 is equal to h nu photon. Energy is incident on the excited state atom. The atom stimulates from higher energy level to lower energy level with emitting two photons. This phenomena is called stimulated emission of radiation. So, due to the stimulated, it is moving higher energy level. At a higher energy level, it absorbing photon energy and stimulates from higher energy level to lower energy level with emitting two photons. Radiation phenomena is called stimulated emission of radiation. So this is called stimulated emission of radiation. So you can see here already we discussed stimulated emission of radiation. Let a photon E2 minus E1 is equal to h nu photon energy is incident on the excited state atom before 10 to the power minus 8 seconds. The excited atom absorbs all the photon energy and stimulates from higher energy level to lower energy level with emitting two photons. This is incident photon, this is emitted photon. Emitted photon. So let a photon of energy 2 minus E1 is equal to h nu interacts with the excited atom within their lifetime. The atom gets de-excitation into the ground state by emptying of additional photon. Additional photon means one incident photon and extra photon, that is emitted photon. This phenomena is called stimulated emission of radiation. It is the process of de-excitation of atoms. You can see about this process. It is the process of excitation of atoms into ground state from excited state by interacting with an additional photon within its lifetime by emptying of additional photon. You can see up to here, this is additional photon. Stimulated emission rate depends upon the number of atoms available in the excited state. The number of atoms per unit volume is called N2. This is N1. This is N2. So what we are discussing, let us take two energy levels E1 and E2. E1 is the ground state energy, E2 is the excited state energy. N1 is the population in E1, N2 is the population in E2. So N1 is the number of atoms per unit volume in ground state. N2 is the number of atoms per unit volume in excited state. So the stimulation rate depends upon the number of atoms available in the excited state as well as energy density of photons. That is, this is rho v. So the stimulated emission rate directly proportional to N2 and also rho v. Rho v is the number of photons per unit volume. Number of photons per unit volume. So we can write this is N2 into rho v. So proportionality constant B to 1, the atom coming from N2 to N1. So we are taking B to 1, N2 rho v, where the B to 1 is known as Einstein's coefficient of stimulated emission. Stimulated. Okay, coming to the characteristics of stimulated emission. So already we discussed about this. You see here, we discussed this is characteristics of stimulated emitted radiation. So this is N1, this is N2. The emitted radiation is monochromatic. The emitted radiation is coherent. The emitted radiation is high intense light ray. The emitted radiation high directional. Examples: light from the laser source. Light from the laser source. This is the stimulated emission of radiation. Stimulated emission of radiation. So, what is the definition? The excited state atom can stay up to 10 to the power minus 8 seconds. Before 10 to the power minus 8 seconds, E2 minus E1 is equal to h nu photon energy is incident on the excited state atom. The excited state atom stimulates from higher energy level to lower energy level. Higher energy level E2 to lower energy level E1 with emitting two photons. Incident photon and emitted or emitting photon. Emitting photon. This phenomena is called stimulated emission. So before 10 to the power minus 8 seconds, if E2 minus E1 is equal to h nu photon energy is incident on the excited state atom, the excited state atom stimulates from higher energy level to lower energy level, stimulates the atom from higher energy level to lower energy level with emitting two photons. Phenomena is called stimulated emission of radiation. Before 10 to the power minus 8 seconds, E2 minus E1 is equal to h nu. Photon energy is incident on the excited state atom. The excited state atom absorbs all the photon energy and stimulates the atom from higher energy level to lower energy level with emitting two photons. One is incident photon and another one is emitted photon. Phenomena is called stimulated emission of radiation. The stimulated emission rate is directly proportional to population in excited state or the number of atoms per unit volume in excited state or number of photons per unit volume rho v. So we can write directly proportional to N2 into rho v. So proportionality constant B to 1 N2 rho, where B to 1 is Einstein's coefficient of stimulated emission. So the emitted photon radiation is high monochromatic, or the emitted radiation is monochromatic, the emitted radiation is coherent, the emitted radiation is high intensity, high directional light source. Example, light from laser source. So this is the stimulated emission of radiation. So we discussed absorption, spontaneous emission of radiation, stimulated emission of radiation. What is the main difference between spontaneous emission and stimulated emission of radiation? Okay, this is spontaneous emission of radiation. This is stimulated emission of radiation. The spontaneous emission was postulated by Bohr. The stimulated emission was postulated by Einstein. Second point, additional photons are not required in spontaneous emission of radiation. So additional photons are required in stimulated emission of radiation. For example, additional photons means, for example, E2 minus E1 is equal to H nu photon is incident in the excited state atom. But in spontaneous emission of radiation, there is no incident of photon in the excited state. So no need to additional photon for spontaneous emission of radiation. After 10 to the power minus 8 seconds, the atom returns to the ground state by itself without incident of any photon. So here there is no need for additional photons. Additional photons are not required. But in stimulated, additional photons are required in stimulated emission. So in spontaneous emission of radiation, only one photon is emitted in spontaneous emission, but two photons are emitted in stimulated emission of radiation. The emitted radiation is polymonochromatic, but in stimulated emission of radiation, the emitted radiation is monochromatic. In spontaneous emission, the emitted radiation is incoherent. In stimulated emission of radiation, the emitted radiation is coherent. Coherent. The emitted radiation has less intensity. Here it has high intensity. The emitted radiation have less directionality. The emitted radiation have high directionality. So this is the example for spontaneous, that is light from sodium lamp or mercury lamp. You can see clearly sodium lamp or mercury lamp. For stimulated emission of radiation, light from laser source, you clearly understand. Distinction between spontaneous and stimulated emission of radiation. So left side spontaneous emission of radiation, right side stimulated emission of radiation. The spontaneous emission of radiation postulated by Bohr, but in stimulated, that is Einstein. So not required the additional photons in spontaneous emission of radiation. So in stimulated, additional photons are required in stimulated emission. One photon is emitted in spontaneous emission of radiation, but in stimulated, two photons are emitted. The emitted radiation is polymonochromatic. In stimulated emission, it is a monochromatic radiation. Spontaneous emission is incoherent light, emitted radiation is coherent. The emitted radiation is less intensity. Spontaneous emission has less intensity. Stimulated emission has high intensity. Or simply, the emitted radiation is high intensity. Population is represented by n. N is equal to n naught exponential of e to the power minus e by kbt, where n naught is the population in energy level E. So already we discussed E1, E2 energy levels. This is N1, this is N2 energy levels. So I am taking at the place of N1, this is N0. At the place of this one, I am taking E. So I am taking here, this is N0, this is N, this is E. So this is excited, this is E naught, this is E. So n is equal to n naught e to the power minus e by kbt. Kb is the Boltzmann constant. T is the absolute temperature. Temperature. So this is the population. You can see here one problem in population. A particle, hypothetical atom has two atomic levels spaced by 3 electron volts in energy. Calculate the ratio in higher energy and lower energy at 50 degrees centigrade. So you can see here that problem. A particle, hypothetical atom has two atomic levels spaced by 3 electron volts in energy. Calculate the ratio of higher energy and lower energy. Actually, try to understand this is N1 lower, this is N2. N1 is the lower energy level E1, N2 is the higher energy level N1. So we need to calculate N2 by N1. Actually, we know N is equal to N naught e to the power minus e by kbt. So this is 2, let this is 1. N2 by N1 is equal to e to the power minus e by kbt. First calculate E value and substitute KB value and D value, T value. We can get that answer. You can see here. So we need to calculate the temperature in Kelvin. So what is the relation? Capital T is equal to small t degree centigrade plus 273.15 Kelvin. So is equal to 323.15 Kelvin. So calculate, we need to calculate KT after getting T KT. K Boltzmann constant. What is Boltzmann constant value? KB or K? 8.81 8.617 into 10 to the power minus 5 electron volt per Kelvin. So substituting K into T, substituting the K value, this is K value, this is T value. So we get KT 0.027 electron volts. So the ratio, calculate the ratio in higher energy and lower energy. This is higher energy, this is lower energy. So we can write N2 by N1 is equal to e to the power minus e by kT or kBT. So this is formula. Substituting e to the power e by kBT, kB into T. So this is 3 already given, E value given 3 electron volts. So I am substituting at the place of E, this is 3. KT, I am substituting 0.027. So we get after calculation, this is e to the power minus 100 and 11.11. So after calculation, this is 1.1 into 10 to the power minus 49. There is no unit because this is a ratio. So try to understand again. A particle, hypothetical atom has two atomic levels, that is N1, N2, or E1, E2. So you see here, the energy is 3 electron volts. E is equal to 3 electron volts. Calculate ratio in higher energy level to lower energy level. So formula N2 by N1 is equal to e to the power minus e by kT. So we need to calculate, given T degree centigrade is equal to 50 degrees centigrade, but capital T is equal to T degree centigrade plus 273 simple or 273.15 perfect. So T degree centigrade 50 degrees. This is 273.15. We get capital T value 323.15. But we know this is Boltzmann constant value K 8.86 into 10 to the power minus 5 electron volt by Kelvin. So substituting KT. Already this is Boltzmann constant K into T value. This is T value. So after calculation KT is equal to 0.027 electron volts. The ratio you know very well. This is the formula N2 by N1 is equal to e to the power minus e by KT. E to the power minus e, this is 3 electron volts, substituting as it is. KT 0.027 already substituted. So e to the power minus 11111, that is approximately is equal to 1.1 into 10 to the power minus 49. So next problem, we can see here a laser medium at a thermal equilibrium temperature of 300 Kelvin has two energy levels with a wavelength separation of 1 micrometer. Find the ratio of population density of the upper and lower levels. So same formula N2 by N1 is equal to e to the power minus e by kT. You see the solution. Ratio of population density, wavelength, 1 micrometer at 300 Kelvin. So lambda given 1 micrometer. 1 micrometer means 10 to the power minus 6 meters micro. So we wrote here 10 to the power minus 6 meters. So energy hc by lambda. This is Planck's constant h value 6.626 into 10 to the power minus 34 joule second. This is light velocity 3 into 10 to the power 8 meter per second. All divided by lambda 1.1 into 10 to the power minus 6. So we get in joule, this is 1.986 into 10 to the power minus 19. So E is equal to 1.986 into 10 to the power minus 19 joules. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. 1 joule is equal to 1 electron volt by 1.6 into 10 to the power minus 19 electron volts. Already I wrote here. So here this is step 1.986 into 10 to the power minus 19, 1 joule. At the place of this joule, I am substituting 1 electron volt by 1.6 into 10 to the power minus 19. So we get 1.24 electron electron volt. So Kt, this is Boltzmann constant K value. Already T 300 Kelvin given 300 Kelvin. So after calculation, the Kt is equal to 0.0259 electron volts. Ratio formula N2 by N1 is equal to e to the power minus e by kBt. Substituting all the values, e value, you can see this is 1.24 here substituting. Remaining Kt, this is 0.0259 electron volts. After calculation, that is equal to e to the power minus 47.96, that is approximately is equal to 1.6 into 10 to the power 21. So I am explaining, you try to understand. So what is the problem? A laser medium at a thermal equilibrium temperature of 300 Kelvin has two energy levels. So E1, E2, it has two energy levels, which wavelength is 1 micrometer. 1 micrometer. That is equal to 10 to the power minus 6 meters. This is N1, this is N2. Okay. So given wavelength, lambda is equal to 1 micrometer. Micro means 10 to the power minus 6 meters. So need to calculate E because e to the power minus E N2 by N1 is equal to e to the power minus E by kT. We need to calculate E value and kT value. So E hc by lambda, substituting all the values. This is Planck's constant, this is light velocity, this is given wavelength. So after calculation, we get 1.986 into 10 to the power minus 19 joules. Joules. 1 joule is equal to 1 electron volt by 1 electron volt by 1.6 into 10 to the power minus 19. After calculation, we get 1.24 electron volts. So calculate the ratio. We get here kT value ratio. N2 by N1 is equal to e to the power minus e by kpt. Substituting e value 1.24 and kT value 0.0259, that is equal to e to the power minus 47.96. Approximately this is 1.3 into 10 to the power minus 21. So next, you see here population, already we discussed population inversion. So population, the number of atoms per unit volume in an energy level, that is called population. What is population inversion? So you know very well, this is N1, this is N2, this is E1, this is E2. So the condition N2 is greater than N1. That condition is known as population inversion. At a particular instant of time, N2 becomes greater than N1. This condition, N2 greater than N1, is called population inversion. Population inversion. What I am saying, let us take E1 and E2 two energy levels. E1 is the ground state energy. E2 is the excited state energy. N1 is the population in E1. N2 is the population in E2. So definition, at a particular instant of time, N2 becomes greater than N1. This condition is known as population inversion, or N2 greater than N1 is called population inversion. So pumping. To achieve the population inversion is called pumping. Population, the number of atoms per unit volume in an energy level is called population. At a particular instant of time, N2 becomes greater than N1. This condition N2 greater than N1 is called population inversion. To achieve the population inversion is called pumping. Pumping. These are the basic definitions in laser. So, what we discussed in this video, we try to see here. So, very starting, we discussed in this video the distinctions between ordinary light and laser light. Ordinary light and laser light. The ordinary light emits the radiation in all the directions without phase relation and frequency relation. But in laser light, the light emits the radiation only in one direction with phase relation and frequency relation. So we discussed clearly the distinctions between conventional light and laser light. So after that we discussed the characteristics of laser. What are the characteristics of laser? We discussed characteristics of laser. So the main characteristics of laser: monochromaticity, coherence, directionality, intensity. What are the characteristics? Laser light has coherence, directionality, monochromaticity, and intensity. We discussed. After that, we discussed the population inversion and pumping. Before that, we discussed the spontaneous emission of radiation, stimulated emission of radiation. So before that, we discussed absorption, stimulated emission of radiation. Clearly we observed absorption definition. If E2 minus E1 is equal to h nu photon energy is incident on the ground state atom, the ground state atom stimulates from lower energy state to higher energy state phenomena is called absorption or stimulated absorption. We discussed it. So next, spontaneous emission of radiation. In the excited state, the atom can stay up to 10 to the 4 minus 8 seconds. After 10 to the 4 minus 8 seconds, the atom returns to the ground state by itself. Phenomena is called spontaneous emission of radiation. We discussed clearly about spontaneous emission of radiation. So, in the excited state, excited state, the atoms cannot stay long time. After 10 to the 4 minus 8 seconds, the atoms returns to the ground state by itself. Phenomena is called spontaneous emission of radiation. This is stimulated emission of radiation. Already we discussed the spontaneous emission of radiation. So going to discuss stimulated emission of radiation. Before 10 to the 4 minus 8 seconds, E2 minus E1 is equal to h nu photon is incident on the excited state atom. The excited state atom absorbs all the photon energy and stimulates from higher energy level to lower energy level with emitting two photons. One is incident photon and another one is emitting photon. These two photons are having same frequency, same amplitude, phase angle difference. These photons emits the radiation only in one direction. This is the this radiation is known as laser light. This phenomena is called stimulated emission of radiation. So after that we discussed the distinctions between spontaneous emission of radiation and stimulated emission of radiation. Spontaneous was postulated by Bohr, stimulated Einstein. In this process, in spontaneous emission, additional photons are not required, but stimulated additional photons are required. One photon is emitted in spontaneous emission. Two photons are emitted in stimulated emission. So, spontaneous emission of radiation is polymonochromatic, incoherent, less intense, Less directional light ray is known as spontaneous emission of radiation. But the stimulated emission, the emitted radiation is monochromatic, high coherent, high intense, high directionality. Radiation is known as stimulated emission of radiation. So after that we discussed the population, population inversion and pumping. In that also some definitions active media or active system. A system which is having longer lifetime is called active system. Lifetime. The excited atom in the excited energy level can stay up to 10 to the power minus 8 seconds. This time is known as lifetime. The excited state atom can stay up to 10 to the power minus 8 seconds only. The excited atom in the higher energy level can stay up to 10 to the power minus 8 seconds. This time is known as lifetime, metastable state. An energy state which is having large lifetime, that is called metastable state. So population, you know very well. The number of atoms per unit volume in the energy level is called population. So we discussed problems also. This is one problem and this is second problem. What is population already discussed? The number of atoms per unit volume in energy levels are called population. Population inversion. Population inversion. At a particular instant of time, the excited population N2 becomes greater than the ground state population N1. This condition N2 greater than N1 is called population inversion, pumping. To achieve the population inversion is called pumping. Pumping. So these are the basic definitions, and also we discussed the absorption, spontaneous emission of radiation, stimulated emission of radiation, distinction between spontaneous emission of radiation and stimulated emission of radiation, characteristics of laser light, distinctions between ordinary light and laser light, and we discussed lifetime, metastable state, population inversion, and pumping. So thank you one and all. Thank you so much.